Welcome everyone. I think we can start. Today, Beren Hoca is with us and she will be talking about her field of expertise and sharing her experiences along with her studies. Her research interests are mainly biomedical signal processing, wearable device design, artificial intelligence, applied machine learning, and data science. Also, she has recently established physiological analysis and wearable systems research lab. And today's topic is wearable devices and artificial intelligence in healthcare. Hocam, we're so excited about the topics you'll be talking about. Maybe we can start if you want.
Okay, thank you. Let me share my screen first. Wait. Okay, I guess everyone can see my screen, right? And hear me? Okay, great. So, hello everyone, good evening. I hope you're all doing well and staying safe. Please be careful, it's really crazy out there right now, about this, COVID-19 situation. So please be careful, try to isolate yourself. So I'm Beren Semiz, and I'm an assistant professor of electrical and electronics engineering at Koç University. Of course, first of all, I want to thank Koç University Artificial Intelligence and Robotics Society for inviting me to this talk. Today, I will mainly talk about wearable devices and artificial intelligence in healthcare. Of course, when we say artificial intelligence in healthcare, there are many different topics under this umbrella term. I will mainly focus on what I am doing, and I will briefly talk about this whole biomedical and health informatics field. And following that, I will show you some sample projects so that you can visualize what's going on behind all these different projects, all these different applications. By the way, some of you might know me and some of you might not. In spring semesters, I'm teaching Comp 125 programming with Python course. And in fall semesters, I'm teaching biomedical signal processing. Actually, we just started to offer that course this semester, so it's a new course. So if you guys are interested in biomedical signal processing, biomedical signal analysis, etc., you can take that course in your junior or senior years, okay? So, yes.
Want to be able to give Comp 125 course again?
In spring semester, I will give Comp 125 again.
In next spring semester,
Next
right?
spring, yeah, next spring semester.
Thank
you. No problem. So a little bit about myself. So fun fact, I graduated from Koç University as well. In 2016, I graduated from Electrical and Electronics Engineering Department. And following that, I directly started my PhD degree at Georgia Tech in the United States. So this was this combined program. So I directly started my PhD degree, but while I was working towards my PhD degree, I received my master's degree as well. And in December 2020, I finished my studies there and I returned to Turkey. Then I started to work at Koç University. I have been working here since January 2021. So I just completed my first year. I'm pretty excited to be back. And I hope that you will be able to take courses from me so that we can meet and interact. And whenever you have questions about life at Koç, about my research, etc., you can always reach out to me. Okay. So let's start with this whole biomedical and health informatics field. So to summarize, in one end, we have the technology experts who know how to develop devices, low-cost sensors, and algorithms, but they don't know how to make an impact in the healthcare industry. And on the other hand, we have the healthcare experts who know the issues in their domain and they know what people need, but they don't know how to adapt this new technology into the healthcare system. So basically, this biomedical and health informatics field tries to fill this information gap between these two groups. Okay, so we try to be that bridge between these two groups. And for this aim, in our projects, we are proposing novel sensor modalities, which enable unobtrusive and non-invasive collection of physiological signals from the body. Then we develop some algorithms to extract some useful information from the signals we are collecting. And finally, we use this information to derive digital biomarkers. So I will talk about this digital biomarker term in a minute, but basically using some tools like biomedical signal processing, machine learning, data science, etc., we are trying to derive these digital biomarkers. And as you can guess, collaboration is a key thing in our research, because we are trying to quantify human health. We are trying to derive some information about human health. That's why we keep collaborating with different universities and hospitals, etc. And in my PhD degree, I collaborated with Emory University, Children's Healthcare of Atlanta, University of California, San Francisco, and Northwestern University. And currently, we have many collaborative projects going on with Koç University Hospital. So am I getting some questions in the chat, or is it something different? I cannot see the... Oh, okay, the questions. Okay, so let's continue. And as you can guess, this field is interdisciplinary by nature, and it's at the intersection of many different fields, such as electrical engineering, biomedical engineering, medicine, computer science, etc. Like, we get help from many different domains, and we can list these domains as medicine and physiology, control systems, embedded systems, and analog circuitry and sensors. So with the help we are getting from these different domains, we are coming up with these novel modalities, novel analysis tools, etc. And our fundamental aim is to achieve continuous health monitoring and treatment titration. And we believe that the way to do this is through deriving these digital biomarkers. Okay, so I kept saying digital biomarkers. Let's briefly talk about what a biomarker is. Then we can continue with this digital biomarker term. Okay. So, according to the definition by National Institutes of Health in the United States, biomarkers are measurable and quantifiable indicators used in evaluating normal versus pathologic processes or therapeutic biological responses to therapeutic interventions. And all the diagnosis and treatment titration for any disease or injury are mostly achieved with these conventional biomarkers. Unfortunately, they require periodic hospital visits and expensive laboratory tests. So just think about this. Let's say you go to a hospital to get your blood test done, okay? The results will be biomarkers. Or let's say you undergo this exercise test. Again, the results of this exercise test will be a biomarker, okay? Or let's say you are getting these imaging tests, such as computed tomography or MRI, etc. Again, the results of these tests, they will be biomarkers, okay? But there is this one slight problem with these conventional biomarkers. So the thing is, you need to visit hospitals in order to get information about your health, in order to get information about the levels of some specific biomarkers. So, okay, you visited hospital and you received some information about your biomarkers. Then, let's say 3 months later, you visit hospital again, and again, you get some information about your health, about your biomarkers. But you don't know what's going on in between these two hospital visits, okay? So you don't know whether you're getting better, whether you're getting worse, whether you need to change the dose of your medication, or whether you need an additional surgery, etc. You don't know what's going on there. There is this information gap. And that's why these conventional biomarkers sometimes fail to provide proactive and preventative treatments, because you cannot catch any worsening situation going on in between these hospital visits. That's why there is a compelling need for novel modalities which can employ continuous and non-invasive health monitoring outside the physical confines of the clinic. And basically, this is our main motivation here. We are trying to achieve continuous health monitoring so that we can we can monitor human health continuously, and we can check whether there is any worsening condition in the physiological states of human beings. Okay, so this is the main motivation behind our research. And what about digital biomarkers? Of course, thanks to the recent advancements in sensor technology, it's now possible to embed various sensors into electronic devices, which enable non-invasive and unobtrusive collection of physiological signals. And these signals carry information that is in many cases complementary to electrophysiology, biomechanics, and movement. And they are really subject specific, and this situation makes them great tools for personalized treatments. And once we collect these signals properly and accurately, we can convert these signals into clinically useful metrics through some analysis tools, such as machine learning, deep learning, data science, etc. Using these tools, we can convert these signals into clinically useful metrics. And basically, we call these metrics as digital biomarkers. And this remote health monitoring concept is actually not something new. It started in 70s and 80s with the term telemedicine, with telehealth. And now we call this whole digitization of healthcare industry as digital health. Of course, many advancements have contributed to this transition, such as internet, mobile devices, smart devices. They all contributed to this digitization of the healthcare industry. So this is what happened in the hardware parts. And what about the analysis part? Of course, we started to work with this artificial intelligence concept. So probably you know about the definition of AI, but basically it's the technology that enables machines to produce solutions to complex problems by imitating the way that humans think. Okay, so we are trying to identify the meaningful relationships in the data we have. So for example, let's say we have these physiological signals. We investigate the relationship, investigate the meaningful information within these signals, and we try to map that information to the target aim we have. This can be detecting a specific disease, or let's say this can be mapping the signal characteristics to medication doses, or it can be tracking treatment titration. It really depends on what your target aim is. Okay, so basically we're trying to build these relationships. And in the healthcare industry, there are many different use areas, application areas of AI, of artificial intelligence. We can group these as disease diagnosis, AI-assisted surgeries, drug development, personalized treatment, and gene editing. Of course, it's not possible to go through all of these in this 40-minute talk, but what I'm basically doing is that mainly I work on disease diagnosis. Of course, the end result is personalized treatment as well, but the main topic I'm working on is disease diagnosis, and I will show you some sample projects about this specific topic. Okay. So in my research, we mainly work with acoustic and vibration signals. Acoustic and vibration signals we get from the body. So just a brief background on what they mean. So when we say sound, basically it's a form of energy originating from the vibration of particles. Say acoustic and vibration signals, we don't refer to the same thing. They are of course different. Basically, we distinguish these two different signal types by the frequency content they have. Okay, so we refer to the signal, the audible frequency range, which is within 20 hertz to 20 kilohertz, as acoustic signals. So these are your heart sounds, for example. You can actually hear your heart beating, or these can be the joint sounds. When you perform this flexion extension exercise, you may hear those clicking sounds. They are also some acoustic signals, okay? You can hear them with your ear. On the other hand, we have this vibration group. So they fall under the infrasound group. And what we mean by infrasound is that this group has frequency content below 20 hertz. You cannot hear these with your ear. They are not audible. They are vibrations. For example, local chest vibrations or micro movements you have in your body. These are vibrational signals. And they all, of course, correspond to the cardiac mechanism you have there. That's why you can get many meaningful, let's say, metrics, parameters from these signals. That's why we primarily focus on acoustic and vibration signals. So that's great. We can, get some information, information about the acoustical and vibration signals. But how are we going to collect these signals? That's the first step we need to consider, right? So first things first, we can use contact microphones. It's one of the options we can use. So the acoustical energy originating from the underlying physiological events travels to the surface of the skin where it can be acquired as sound. So the thing is, there is this impedance mismatch between the air and fluid-filled tissue. So only a small amount of energy can propagate to the air, and most of the energy is reflected back to the tissue. That's why most of the energy is still within the tissue. So when you use this contact microphone, you can actually capture that information, that non-attenuated signal, directly from the surface of the body. So contact microphones are one of the options that we can use to collect these vibrational or acoustical signals. What about another option? We can also use digital stethoscopes. Of course, you cannot use this in a wearable system because it's itself a device. But sometimes in the research, when you read papers, you will see that researchers are using digital stethoscopes to get acoustical information about your body. So this is a bit different than normal stethoscopes because digital stethoscopes can actually record what you're listening to. That's why you can post-process the signals you're collecting. So digital stethoscope, it's another possibility. And finally, we have accelerometers. Accelerometers are the most commonly used sensor type in wearable system design. So you can mount, you can place these accelerometers using textiles, adhesives, or plastic mounting. It really depends on how you're going to design your wearable system, okay? And also you have accelerometers in your smart devices, such as your smartphone, your smartwatches, etc. And you can get information about the physical activity and posture, etc. You can also get information about those things using accelerometers. But here, we are talking about really sensitive accelerometers. They can capture the vibrations you have on your chest, for example. And depending on the application, either a triaxial or a uniaxial accelerometer can be used. When we use a uniaxial accelerometer, we capture vibrations in only one direction, okay? So for example, only in this direction. But when you use a triaxial accelerometer, we can capture these vibrations in 3 different axes, in 3 different directions. So head to foot direction, dorsoventral direction, and lateral direction, okay? Or with simple terms, you can just say XYZ directions. And especially in a cardiac health assessment, using all 3 axes is really important. Although the most information is embedded in this dorsoventral direction, still researchers showed that we can also get some meaningful information from head to foot and lateral axes as well. That's why it's important to use a triaxial accelerometer in applications like this. So that's great. Let's say we captured our acoustic and vibration signals. So what's next? of course, we need to analyze these signals, right? But the problem is when we first collect these signals, they won't be in their perfect shape. Okay, they won't be ready for feature extraction and let's say machine learning or deep learning models. That's why we need some pre-processing steps. We need to prepare our signals for further analysis. And what we mean by pre-processing is that we may perform filtering, we may perform normalization. These are just some sample steps you can take. For example, when you filter your signal, you can get rid of the unwanted noise. Or if you want to work with a specific frequency range, for example, again, you may need to filter your signal. Or let's say you may window your signal in order to capture the small changes in the signals better. So what this means is that instead of using the whole signal, you're using small chunks of this signal to process. Okay. One quick example here, we have a noisy signal and a clean signal. And as you can see, when we get rid of the noise we have, when we get rid of those oscillations, let's say, it will be easier for us to see the important points in this electrocardiogram signal. So this electrocardiogram signal is one of the most important signals, one of the most important physiological signals. Probably you heard about this. You can get information about your heart rate, about your rhythm, etc. But as you can see, when you filter your signal, everything will be more clear. So what's next? Then we need to identify the unique, Then we need to identify the unique characteristics in these signals, okay? And in order to do this, we need to look for some specific features in these signals, such as statistical features, time domain features, frequency domain features, etc. Of course, these features highly depend on your application and your end goal. So it will, of course, change from one application to another. But the important thing is that we need to identify the unique characteristics of these signals. For example, let's say we have these 3 vibration signals from 3 different subjects, okay? So these are chest vibration signals. As you can see, their amplitudes are different, number of peaks are different, the intervals, durations between consecutive peaks are different. So these are all differences in these signals. So assume that we need to detect a specific disease. Maybe we can leverage these features in order to build our machine learning model. Okay, it's just an example, I just made it up. But as you can see, the important thing is to see the differences in these signals. And following that, we need to learn the relationship between these features and our target aim. Okay, as I said, it can be detecting a disease, it can be estimating, let's say, blood pressure values. It highly depends on your application. You can use some data analytics methods, machine learning methods, some statistical analysis, etc. Of course, there is another type of analysis you can perform. Instead of extracting features, you can directly skip to the final part, and mostly deep learning methods use this. So you don't need to extract features for deep learning models. You can directly feed your signals to your deep learning model so that you will end up with the target results you have, okay? So this is the analysis part, and this is what I'm teaching in my biomedical signal processing course. I will be offering that course in fall semesters. So if you're curious about, analyzing physiological signals, you can take that course. And of course, in addition to instrumentation and analysis parts, we also have this sensor feedback and patient feedback part, but it's ongoing research. Of course, it's something different, but overall, our steps include, our analysis framework includes these steps. There are too many steps we need to consider. So enough with background information. Now let me briefly show you some sample projects so that you can visualize what we are actually doing. So first of all, I will talk about wearable acoustic and vibration measurements for cardiovascular health assessment. And for this one, I will mainly focus on the vibrational signals. So our application is non-invasive hemodynamic monitoring. So what I mean here is that we will focus on some hemodynamic parameters. We will try to estimate some hemodynamic parameters. And for this project, we focused on the stroke volume value, okay? So stroke volume is the volume of blood pumped from the heart per beat, okay? So you don't really need to know the definition of that, but it's an important hemodynamic parameter for us, okay? And especially it's really important to track the stroke volume values during surgery. And during surgery, the best way to do this is to use this Doppler system, okay? But as you can see, in order to use this Doppler system, there should be this probe, this tube-like small thing inserted through your esophagus, through your mouth and through your esophagus, which means that this is an invasive procedure. So there should be something inserted through your mouth. So it's an invasive procedure. Also, there should be a trained professional to use this system, okay? And of course, this means that you cannot use this Doppler system when the surgery is over. But the problem is tracking stroke volume values after the surgery is also really important. That's why we need a non-invasive alternative to this Doppler system, which can be used for monitoring stroke volume in patients during and after surgery, okay? So instead of this bulky invasive Doppler system, our aim was to come up with a non-invasive device to track the stroke volume values, okay? This was the main idea of this project. So for this project, we collaborated with Northwestern University. This project was one of the projects I did during my PhD degree. So we collaborated with Northwestern University and we came up with this wearable patch. Okay, so this patch is really small. It has this, it has a size of 10, it has a diameter of 10 centimeters, and it only requires 3 electrodes to mount on the chest. And the good thing about this device is that it was recording 2 important signals continuously. The first one is the well-known electrocardiogram signal. Once you process the electrocardiogram signal, you can get information about heart rate, rhythm, etc. And the second type of signal was the seismocardiogram signal. And in order to capture this seismocardiogram signal, we used an accelerometer. What we mean by seismocardiogram signal is that basically we refer to the local chest vibrations, okay? So they are these small chest vibrations. You cannot feel it, but an accelerometer can capture it, okay? And if you use a triaxial accelerometer, you can capture those vibrations in 3 different directions, as I previously mentioned. So electrocardiogram signal assesses the electrical activity of the heart, and these vibration signals, they assess the mechanical activity of the heart. That's why using these different signals, we can get information about both the electrical and mechanical activity of the heart. So following that, of course, we had to work on an analysis pipeline. So while the patients were undergoing surgery, the Doppler system was recording the actual stroke volume values, and our patch was recording 2 of these signals, I mean, seismocardiogram and electrocardiogram signals. And following that, we performed some pre-processing steps, as I previously said. So we performed filtering, windowing, averaging, etc. And following that, we extracted some amplitude and timing features from the signals we obtained. So the reason why we extracted amplitude and location features was that the peaks and valleys on these seismocardiogram signals correspond to some specific physiological events, such as aortic opening, isovolumetric contraction, etc. So actually, these, as you can see in that SCGZ1, actually these peaks mean something. That's why while we are analyzing our signals, we extracted the amplitude and location features, and following that, we fed these features to a regression model in order to predict the stroke volume values. So while working on an application like this, we usually use a method called leave one subject out cross-validation. So what we mean here is that in each fault, we leave all data from one subject out, and we train our model on the data of the remaining subjects. And then we test our model on the data of the subject being left out. And we complete this for all subjects until we are done with, until we test the data from all subjects, okay? And when we do that, we of course had some predicted stroke volume values. And we also knew the actual stroke volume values. So we just checked the correlation. We just checked the error we have there. And we saw that our error was really low and our correlation was pretty high. So we can say that actually our method worked. Actually, our regression model worked well in estimating stroke volume values. And one other approach is that in applications like this, sensor fusion is important. What I mean by sensor fusion or signal fusion is that, for example, when I used only one axis features, as you can see, the correlation was really low. But when I used features from different axes, such as X, Y, Z axes, the correlation increased. So this actually shows the importance of using multiple signals in an application like this. And this is actually, the sentence is just summarizing what we did there. So when we combine these physiological signals, these vibrational signals and the ECG signal features, we can calculate the stroke volume values with sufficiently high correlation. So this was just a pilot study, by the way. We only had around 12 or 13 subjects. That's why we could easily perform leave one subject out cross-validation. But of course, if we had more subjects, then our analysis method would change. So it's really important to choose a method depending on your data set, depending on your application, okay? And another project I will talk about is wearable acoustic measurements for biomechanics. So in the first project, we talked about vibration analysis. This time I will talk about acoustic analysis. So this time we will focus on knee, okay? Knee is one of the most complex joints in the body, and it is subject to this extreme force. That's why it's subject to injuries. Also, it's subject to many different diseases. And for this project, we primarily focused on the arthritis disease or joint inflammation. In Turkish, we call it as arthrit. Probably you guys heard the term before. So the most common disease affecting the knee is arthritis. And indeed, there are both invasive and non-invasive methods for knee health evaluation, but they are really expensive. And in order to get these tests, you need to visit hospital again. But in the literature, use of acoustics has proposed. And in this project, we focused on the use of acoustic analysis. So during active movements like flexion and extension, as I previously said, vibration signals are emitted from the mid patella, and these vibrations can be measured on the surface of the skin as sound, okay? So you can actually hear your knee clicking. If you do that flexion extension exercise, you will hear that your knee is clicking. Of course, the clicking you will hear will be physiological clicks. I mean, they will be healthy clicks. But if you have a disease like arthritis, or if you have an injury, you will keep hearing these periodic clicks, okay, like click, click, click. So what we did here was that we attached a uniaxial accelerometer, because this time we only needed one direction, a uniaxial accelerometer to the knee, and we collected the joint sounds from subjects while they were performing flexion extension exercises, okay? And here you can see an example recording from a subject with arthritis and a recording from a healthy subject. As you can see, when you have this joint inflammation, when you have arthritis, you will hear these periodic clicks, okay? So they will have this spike-like appearance in the time domain plot you have. This will be the clicks you are hearing. And in the frequency domain, again, there are some important characteristics. First of all, the frequency content reaches up to 20 kilohertz. That's why you can also leverage some frequency domain related features in the analysis as well. So this time we performed a classification task because we wanted to distinguish between healthy knees and knees with arthritis. So we extracted some frequency domain and time domain features this time because we knew that there are some differences in time domain and frequency domain signals. That's why we decided to leverage these features. And we trained a classification model. And actually, we were expecting to see a separation between these two groups, I mean, healthy group and group having this arthritis disease. So in this box plot, the red boxes correspond to the subjects with arthritis and blue boxes correspond to the control subjects. As you can see, as we expected, subjects having arthritis have scores closer to 1, whereas subjects not having any disease, I mean control subjects, have scores closer to 0. So we exactly observed what we were expecting. And secondly, we also tested our model on the post-treatment data to quantify the treatment responses. So we wanted to check whether we can catch the improvements after these subjects received some specific treatment. So as you can see, the scores went below 0.5 and they got closer to 0. This means that we could actually observe these improvements in the joint acoustic signals as well. So we could actually observe the success of these treatments in our model as well, okay? So I just showed these two projects for you to, make things more to make you visualize what we are doing. Of course, these are just pilot studies. We need better validation. We need to work on the noise and error quantification aspects better. Most importantly, we need to standardize our measurements because we were taking these, we were taking this data in controlled, in lab settings. But of course, in an ideal scenario, what will happen? Subjects will be collecting this data throughout the day during their daily life. Of course, there will be, many noise sources, many error sources, or subjects will be placing the sensors at a different location, a wrong location, etc. Of course, we need to take into account all these problems. And there are many directions we can take after this point in order to make these systems ready for actual real life scenarios, okay? But most important, of course, we need better validation. In those studies, we had around 12 or 13 subjects, but of course, we need more subjects in order to validate our models. So another thing is that we need to achieve biomarker phenotyping. So there is this limited one-to-one correspondence between the signal characteristics and the important health parameters. But when the goal is actually to predict the underlying cause or symptom, then we may need more extensive and interpretable biomarkers. So yes, we are extracting some features and building some models, but what do those features actually represent about the underlying physiology? So there is this information gap in this field. So we need to build those relationships better. We need to have these biomarkers more, make these biomarkers more interpretable, okay? So for example, in the joint sounds case, yes, we could distinguish between healthy subjects and subjects having some specific disease, but how would we, for example, distinguish between a subject having a specific disease and another subject having another disease, okay? And one way to do this, and only way to do this, is to study which features encapsulate which symptoms. So we need to achieve this biomarker phenotyping thing. And similarly, if we are working with, let's say, cardiovascular data, of course, we need to be able to quantify different parameters separately, individually, in order to follow them, in order to monitor them individually, because there are many different diseases, many different parameters to monitor. So we need to be able to achieve this phenotyping thing in order to track these different parameters individually, okay? So I'm the director of the Physiological Analysis and Wearable Systems Research Lab at Koç University, and our lab is in the SNA building. So I have both undergrad students and grad students working with me. So we just established our lab actually, so it's pretty new. But yeah, just keep that in mind. If you, like, in your upcoming years, if you're interested in, you know, working things like this, you can always get in touch with me. For example, one current project we are working on is to develop this wearable system in order to capture all those cardio-related information, all those cardio-related parameters together. So in other words, we want to design one device for all. We want to develop this device which can give us information about heart, lungs, blood pressure, vascular health, etc. So we are working on this specific project right now, and we also have some side projects about sleep apnea detection or pain quantification, etc. But this is the main project we are working on right now. And as I previously said, I'm offering this biomedical signal processing course in fall semesters. So if you're interested and if you want to learn about learn more about the analysis part of these systems, you can take this course. But we have this prerequisite. The prerequisite is the Signals and Systems course. So after you take that course, if you're interested, you can take my course as well. So that's all from me. If you have any questions, I will be happy to answer them. I guess we have some questions. So I will just stop sharing. Okay. So if you have any questions, I can answer, guys.
Thank you for your presentation. Before we get the questions from our friends, we wanted to ask a question to you. This is a tradition for Beyond the Popular seminars. We want to learn our guests' perspective about this, their advanced topic. So according to you, what is the most misknown concept about AI in healthcare? I mean, what people should know about that, but it is, I mean, it is too overrated or it is too underrated. It is beyond the idea.
So yeah, whenever I give a talk or presentation about my research, the first question I'm getting is, oh, so in the future machines will be doing all these surgeries and machines will be like machines will replace doctors, medical doctors. People keep saying things about this. Maybe in the very further future we might have something like that, but in the near future, of course, it's not possible, because these systems require really these systems require validations, these systems require approvals, these systems, there are too many ethical problems behind these, especially health related data. So I think the misconception, I mean, at least this is the question I keep getting. It's whether machine learning or AI will replace the actual doctors in the future. I think that's the one thing people keep asking me, but maybe in the really further future, but not in near future, trust me, because there are too many problems, too many ethical ethics related or validation related problems in this research field. So not in the near future. I hope I could answer your question. But yeah, I was not expecting this question. Actually, I was expecting this, something related to this, replacing thing. But yeah, thank you.
Thank you, Hocam. Thank you.
Gül, I guess you had a question, right?
Yeah, we
Yes,
can-
Hocam, I have some questions. And to be honest, when you talked, I couldn't understand some parts, so I would like to be sure about them. So I have, I think, 2 questions about this part. Since the devices or sensors you will produce will always be used inside or outside the body, so will be watches like accessories that can be used continuously? If so, what are your thoughts on this subject? This is my first question. My second question is, will the devices which you will design be attached inside of the body, or will they be followed remotely with certain systems? Or will they be monitored remotely with a system in a form of a chip that can be placed inside of the body? This is my questions, actually.
Okay, actually, they are great questions. So I'll start with the second question. So the thing is, actually, in the current project we are working on, we are trying to develop this wearable patch, and it will include this Bluetooth system, and it will directly transfer the data it's collecting to your smart device, so that you can process the signals being collected after this patch records your physiological signals. So the thing is, there will be this Bluetooth system between the actual sensor on your chest and there will be the system which will transfer the data, which will send the data that this patch is collecting. So this is the main idea in our current project, at least. And for the first question, so of course the ideal scenario is to have these devices waterproof, so that they can be worn continuously, etc. But at this stage, these are just in-lab experiments and prototypes. So probably it will take, too much time until we come up with a device like Apple Watch, for example. So it's something different. So they're waterproof, or you can continue to wear them, etc. But for these sensors, of course, they have this, let's say, short battery life, and you cannot, of course, keep that device on while you take shower, or let's say while you're swimming, for example. Of course, the ideal scenario is to have this device which you can wear continuously, but I think it's it's a further research question. Right now we are just trying to get this meaningful information from these systems. I hope I could answer your question. But yes, it's an important topic, but probably that will be in the further future, not in near future, because our fundamental aim now is to have these systems tested in lab environments. Okay, and after that, of course, we can improve our systems, and they can be something like Apple Watch, or let's say other smart devices. Okay,
I understood, but let's in this case, so we need to produce some chips that can be replaced inside of the body.
So that's another that is another aspect, actually. So
in this case we can follow the things that you mentioned.
You're right. But then it won't be non-invasive, so you should have something inside your body. So my field is primarily focusing on designing these non-invasive systems. But if you place a chip, of course it's the research field of some other it's a different research field, but yes, it's also an option. Of course, you can have these small chips inserted into your body, so that they won't be affected from outside environment. But then it will be this invasive procedure. It will be a bit different than our targets. Our fundamental aim there. But you're right. If you have that inserted chip there, of course you can have it continuously. Actually, yeah, that's a great approach.
Okay, thank you so much for your explanations.
No problem.
Good evening.
Good evening.
We can take your questions from chat or by
or you can ask questions about, you know, life at Koç, because I was once a student there. And I graduated in 2016. Actually, I'm not that old, so you can ask questions about student life there or campus life as well. Or let me, oh, you already put that. Okay, I will just type my email in the chat. If you have, you know, some specific questions, you can also, you know, send me an email and we can discuss about those.
So what was your favorite thing in Koç about academical life, about social life?
So
Any
let's see.
Tips for us?
Okay, actually, it's a great question. So the thing is, try to take courses from different majors, because, you know, Koç University is offering this wide range of courses from, you know, many different faculties, many different, let's say, schools. So, for example, while I was a student there, I did a minor in economics. I took some drawing courses. I took Spanish courses. So Koç University is offering a lot. So, you know, try to take different courses, not just focus on your major, but also, you know, try to take some courses from other, let's say, departments as well. Also, if you are curious about research and if you want to continue an academic career, in your third or fourth year, make sure that you're working with one of the professors. I mean, you do research with one of the instructors, one of the professors, because it's really important, especially for your applications. And also it's important to, you know, get that, let's say, feel that research environment, because if you decide to continue in this, you know, academic career, of course, you will spend the rest of your life doing research. That's why if you're, you know, if you are planning to continue with academic career, make sure that you're working with one of the professors. So we really like to work with students, so don't be shy. Just go and knock on the doors of your professors and say, hi, you know, I want to work with you. I'm really interested in your research. Can we talk for a minute, etc. Don't be shy, okay? Never be shy. And another thing, of course, we have this COVID situation right now, but these, you know, Erasmus and exchange opportunities are really good. I hope that COVID will be over soon and, you know, you guys can travel safely. But while I was a student there, I participated in this exchange program at University of Pittsburgh. And it was a great experience, actually, because especially if you are planning to, let's say, go abroad after you graduate, it's a good practice. I mean, it's a good idea to practice whether you want to live abroad or not. And the only way, I don't want to say only way, but the best way to test that is to participate in these Erasmus or exchange programs, because you will stay in a different, let's say, you will live in a different country, in a different city for 4 or 5 years. So it will be a great experience for you. And other than that, yeah, just make sure that, you know, you're enjoying your life at Koç University. We have a great campus. Yes, we had COVID right now, but I hope that it will be over soon. And what I liked the most was the campus life, of course. I mean, like my friends, dormitory life, campus life, different courses I was taking. You know, I was not only taking electrical engineering courses, but I also took other courses, as I previously said. So enjoy your life there, okay? I have a question in chat. Fulbright. Hocam, one day if you give a speech to us like today about Fulbright scholarship, it will be great. Okay, actually, yes, if you are curious about, you know, Fulbright scholarship, you can get in touch with me. We can discuss what that is, what you need to do about that. So for those who don't know about Fulbright scholarship, it's a scholarship, like you apply to the scholarship in your third year, I mean, second semester of your third year. It's for graduate studies in the United States. You can apply to this Fulbright scholarship both for master's degrees and PhD degrees. I applied for the PhD version. So basically, it's a scholarship, but it's a prestigious one. So if you guys are, curious about a Fulbright scholarship, you can also get in touch with me, and we can, chat about the important things regarding this Fulbright scholarship. That's another actually suggestion, recommendation I can give. Do not miss the scholarship deadlines. Try to follow these different opportunities you have around. So Fulbright scholarship is one of them. Also, you have some other scholarships like Fulbright scholarship. So make sure that you're following the opportunities around. Especially right now, the dollar currency is really high. So these scholarships are extremely important for all of us. So make sure that you're following those opportunities. And I think that's all from me. Elif Ayça, I guess you have a question.
Yes, I wanted to ask, the ELEC 201 course is a prerequisite of this, the biosensors course that you're planning to give. I was wondering, the course you are going to give, is it also based on signal analysis mostly, or how much is it similar to ELEC 201?
Okay, so it's a great question, actually. So the thing is, after, in the end of this course, you need to work on a project, and in that project, you will be, you will find a data set, a publicly available data set from these databases such as PhysioNet, etc. And you will analyze these signals. You will come up with this analysis framework. So of course, while working with these signals, you will use filtering, you will use let's say you will use MATLAB or Python. It depends on you, of course. So the thing is, signals and systems course, of course, it has too much, this course has too much information there, but we mostly focus on the application part of those theoretical things. So the first 2 lectures of this biomedical signal processing course actually covers what you have done in signals and systems course as well. So if you like, it's not a solid signals and systems course. So the second part will include machine learning, data science, and mostly we will discuss different physiological signals, etc. But of course, in order to analyze these signals, at some point, you need to apply some filters. You need to, perform some analysis steps, etc. But you won't need like theory-based signals and systems knowledge for this course. Okay, it's mostly applied based. So that's why do not afraid of this course. So it won't have these theoretical background. And I will be reviewing what you have covered in ELEC 201. Also, in this, in fall semester, we had some students who did not take ELEC 201. I'm also okay with that, as long as you know a bit, you know a little about signals and systems. You should be fine. Okay, so it's not a theory-based course. Don't worry.
Okay, thank you so much.
No problem. Okay, any other questions? I guess we don't have any questions, right? Let me check. And if you're planning to take programming with Python, probably I will be one of the instructors. Not probably, I will be one of the instructors, but I will be teaching 2 sections. The professor will be teaching a 3rd section. So I might be your instructor there. So thank you all then for your questions, for joining. As I said, whenever you have a question, you can always get in touch with me. My office is also in the SNA building. So whenever you have a question, whenever you want to chat, you can always stop by my office. Like I really like to chat with students. That's why don't be shy. Whenever you want to ask something, just stop by my office or send me an email. Thank you guys for joining, and I'm leaving the stage to Demet and Chisem.